Welcome to the CEDAR Grand Challenge workshop, Storms and Substorms Without Borders. We would like to improve our system-level understanding of the Magnetosphere-Ionosphere-Thermosphere coupling processes by fostering the collaboration between CEDAR and GEM communities. We wanted to, the reason behind this title is that we wanted to get rid of the artificial boundaries that get in the way of our improvement, such as including high versus mid and low latitude, open versus closed field line regions, modulars versus observations, and CEDAR and GEM communities. So this morning, we invited Bill Lotko as a tutorial speaker from the GEM community. He got his PhD at UCLA. Now he is a Sue and John Ballard 55 TT 56 professor of engineering at Dartmouth College. And he's a chair of Portfolio Review Committee at NSF AGS Division, as you saw yesterday morning, and Focus Group co-chair of Geospace System Science of NSF GEM program. And his main research interest is ion outflow and MI coupling. He has published more than 300 papers. Please let me present Bill to you.
Thank you, Naomi, and also thank you to the Grand Challenge Organizing Committee for giving me the opportunity to talk about some of the work that we've done in this area. It's actually a very tall order. It's hard enough to talk about magnetosphere-ionosphere coupling, put thermosphere in there, and now level on storms and substorms. So I'm going to select some topics to go through to give you some idea of the coupling and the sort of storms and substorms without borders that Naomi mentioned. I'd like to acknowledge many collaborators in this work, and I would say especially Ben Zhang, who's kind of become our resident expert in the simulation work that we've done on this particular topic, and also some useful insights from Roger Varney, who's here today. Okay, first of all, let's motivate it. Why do you want to do it? So why worry about the complications of coupling? I mean, it's hard enough to just talk about the IT system or the mag system, solar wind magnetosphere, so why do we have to worry, or when do we need to worry about it? Well, first of all, these three elements of the system become especially interactive during intense or strong solar wind driving. Model predictions, we're learning, don't do very well without coupling during such intervals. And the utility of our predictions and understanding really depends on the fidelity of the predictions. And in particular, we're thinking about applications like space weather. I see a lot, Josh and I had some back and forth on this recently. I see a lot of goals and objectives say, understand X. And I claim that's almost meaningless, because is your understanding the same as my understanding? Understanding, the rubber meets the road when you can predict, and then you've demonstrated that you truly do understand it. Of course, unless you're using something like a neural net model or something, which is mainly based on a lot of data. And then probably for me, I'll just be honest, I think this is an exquisitely complex and interesting system, and it's fun to study. So what might you learn from this tutorial, speaking especially to the students, and I realize there are people here who are going to already know some of this stuff, and I've always felt that in any kind of talk, that if you hear things that you thought were once true and they're still true, somehow that's reassuring. So anyway, I think in terms of coupling agents, when we talk about coupling between various elements of the system, what's doing the coupling? And there has to be something that's doing that, and those are the agents. And then agents kind of follow pathways, and they're coupled. It's hard to differentiate them. They exhibit feedback, And the two principal modes are electromagnetic and material, but those are coupled because these agents can go from being electromagnetic to material along the pathway of the coupling. And then I hope you'll get some insights into what MIT coupling is, regardless of whether it's storm or substorm. And then I'll spend some time talking about coupling during storms with data model comparisons. So agents of Magnetosphere-Ionosphere-Thermosphere coupling, these are some of the most important ones. I'm not going to claim that they're exclusive, but I have 2 slides worth of them. So the DC downward pointing flux, we know has a big effect. And I mean, if you're going to heat the thermosphere and get the ionosphere moving, that has to be powered in some way, and it's largely powered from the downward DC pointing flux. It's a year of average data for KP larger than 2 from the Astrid 2 satellite to give you a sense of the distribution. These regions over here are where the region 1, region 2 currents close in the ionosphere. That closure has a sigma p E squared, a significant joule dissipation. It's got to be powered by pointing flux coming down. And then over here in the Dayside throat, you have fast flows and a lot of power deposited in the ionosphere as well. Electron precipitation, very important. I think of electron precipitation, it doesn't have as much power as the pointing flux, the DC pointing flux, but it's kind of like the gate on the transistor. When the electron precipitation turns on and becomes more intense, it modifies the conductivity and changes the whole level of interaction. So it's quite important, and we know about diffuse precipitation. These 2 plots are from the Ovation Prime model for winter relatively high driving. And here we see a plot from a recent paper by Hayakorth overlaying time GUVI data in color with 2 sigma field line current contours, the red ones here being upward and the white ones being downward field line currents. And you see that, as is fairly well known, I think, the monoenergetic precipitation. And by the way, this is number flux, but this plot here is indicating energy flux. The energy flux of the monoenergetic precipitation tracks the region 1 current system fairly well, but not on the dawn side, because this is primarily diffuse precipitation, electrons drifting around to the dawn side, gradient curvature drifting. And so they're fairly energetic, fairly important, this effect up here, but they don't track the current systems to the same extent that the mono does. Now, what about the AC pointing flux? Year of data from the polar satellite projected down to 100-kilometer altitude, and we see these 2 hot spots, one up here in the near cusp and one over in the night side equivalent of the cusp, the night side merging throat, or basically not exactly the merging throat, but just equatorward of it. This is bandpass filtered, giving you fluctuations in the period from 6 to 180 seconds. So knocked down quite a bit from the DC pointing flux with power levels quite a bit lower. And one thing that we see is that broadband electron flux, again from the Ovation Prime model, tracks this night side pointing flux fairly well. The altitude range is a little bit different, maybe in part because of the difference in the magnetic field models used for these. We also see that ionospheric outflows, and this is for I also think for a year of data, as I recall from the polar satellite, again projected down to the ionospheric altitude, and you see ionospheric outflows coming out of the cusp here, and then equatorward of the night side merging throat. And I've just overlaid on here convection contours on both of these to give you a sense. These are not actual, the convection contours are not actual data in either of these plots. But one thing that you notice here is that the outflows in the cusp are poleward of where the broadband electron flux is, and we think there's a causal relationship between the power that's coming in this way and the outflows, but because ions are slow, these are lumbering particles moving up the field line, they see that convection field. And by the time they get up to polar, they've already moved poleward of where they've been energized in part. So they're poleward here of where the energization region is, and equatorward here for the same reason on the night side, something that Roger Varney has shown recently in some nice work that he's done. And then the thermosphere exhibits some correlations with these patterns as well, not exactly co-located, and I'll talk about that a little bit later. This is actually a difference between the CHAMP and the EMSIS model for the thermospheric density. And a note to self here, conductance. I wish we had some actual data to show conductance patterns like this, because it is really an important agent in magnetosphere-ionosphere-thermosphere coupling. I think it's one of the challenges ahead of us. So pathways, there's the pathway of particle and electromagnetic energy flow through the MIT system is circuitous, it snakes around, it's complex, but when we get down to the ionospheric level, it's easiest to think in terms of this familiar relationship between the field line current flowing into the top of the main conducting layer of the ionosphere. This is height integrated. The ionospheric potential, and then the conductance. And if we think that the magnetosphere is a current source, then this equation, assuming we know sigma, tells us how to find the potential in the ionosphere and therefore the convection patterns. Alternatively, if we think that the magnetosphere imposes on the ionosphere a voltage, then the conductivity implies some distribution of field line current. The fact of the matter is that you can't really think of one versus the other. The magnetosphere has to shake hands with IT, and if it doesn't, then it's not setting up a self-consistent loop here. So it's it's really mixed when you think about whether it's a current or voltage source. And the spatial distribution of sigma has a very important effect on what comes out of this. And then material transport. And it's harder to show that in an equation, and I borrowed a slide from the AMY panel, which Jeff Forbes might recognize, showing a circuitous path, for example, of O+ outflows and some of the effects that they have. So Joule heating lifts the ionosphere up as well as the thermosphere. And so there's an entrainment of O+ in polar circulation. You can see here GPS TEC plot bringing enhanced flows over the polar cap. The ions are energized, and as I've shown in the agents plots, start moving up the field line, circulate through the cleft ion fountain, mantle lobe into the plasma sheet. They affect reconnection in the night side, and also they can affect it in the day side. Modify the ring current, actually change the solar wind magnetosphere interaction. So the solar wind's the solar wind's a given if you go far enough upstream, but in the vicinity of the boundary, these effects change that interaction. And then there are effects that come back and influence the thermosphere. And I would say there's a lot of work that needs to be done here in understanding the interaction of the thermosphere with the sort of electrodynamic and charged particle aspects of this system. Okay, so I'd like to show some plots that are probably familiar to almost everybody in this audience. These plots are from the Weimer 2005 model, which you can go find at CCMC and generate them with abandon. These three plots here are done for progressively more intense driving, -5 nanotesla, -10, -15, and correspondingly larger solar wind velocity and density. And so these are, given that it's due south statistically, you might expect that for the Dungy cycle that the pattern would look like this, and it does, roughly speaking, but it's got some differences. And I'd like to call your attention to some of the differences we've looked at and tried to understand with new eyes. So stronger driving, we know that the convection is faster and it extends to lower latitudes as you go from left to right in this plot. The location of the Dayside convection throat is offset from noon here, but roughly speaking, it's predicted, at least for conditions of due south IMF, reasonably well by determining where the magnetopause is located, the standoff distance of the magnetopause, which this is the first order approximation, empirical relation by Shu gives a better formula. And these dots indicate the mapped location of where that is, which corresponds reasonably well with what you see here. Okay, so things that are kind of anomalous, to use Michael Mandillo's terms from yesterday. There's a clockwise rotation of the convection pattern when you view it from the North Pole. And there are different ways you might try to quantify that if you just draw a line between the potential minimum and maximum and ask how does that deviate from horizontal up here. It doesn't change much as you ramp up the solar wind driving. There's an excess flux circulation in the dust cell. That's manifest by the fact that the potential in the dust cell has a larger magnitude than the potential in the dawn cell. What does that mean? It means that more magnetic flux is circulating in the dust cell than it is in the dawn cell. What does that mean for the magnetosphere? It's an interesting question, and I'll come back to that a little bit later. And then, of course, we have this famous harangue region here in which the contours kind of stretch eastward and then come back and go westward. And this is a consequence of polarization in the ionosphere, an enhanced conductance channel in which the ionosphere polarizes and produces a different a twist to the convection. Just to be complete, I'm going to go through and give a sense of the differences when you add an IMF-BY. So 45 degrees positive, 45 degrees negative BY here. And these effects are well known to be due to the fact that when you have an IMF-BY, the field lines that go up here and are anchored in the solar wind are yanked tailward by the solar wind flow to first approximation. They're frozen into the solar wind, and so that's pulling the flow over to the side in different directions in northern and southern hemisphere. And you see that the effect here is different for when it's positive as to when it's negative. And some noteworthy features here. There's a very channelized flow here, which has been observed by Sandholt and others when you have strong IMF-BY. Notice that the contours are much closer together here. The flows are much faster in that region. The northern hemispheric cusp and polar cap are pulled duskward. For the other direction of IMF-BY, they go dawnward, and there's not a mirror symmetry here. You know, you'd kind of expect if that Dungy cycle were really exactly how things are, when you flip the direction of IMF-BY, things ought to just be mirror symmetric, but they're not. And then the overflux circulation for the negative BY case actually reverses and now is higher in the dawn cell. And then effect of season and dipole tilt. So you can think of the dipole tilt when it's positive as being summer-like in the northern hemisphere and opposite winter-like here. And so you see that the effect of the rotation is moderated to some extent here. And I'd just like to point out dipole tilt, at least as far as the magnetic field is concerned, is like IMF-BX. However, season adds a whole nother layer to it, which is the fact that the conductance is different in the two hemispheres. So if you were near equinox and you had IMF-BX, it would be, you'd have more or less the same conductance in the two ionospheres, but it would do something similar to these patterns that you see here. And in the summer, you see the rotation is moderated and the overflux circulation is exacerbated. Okay, so let's try and understand some of these things that we see in typical convection patterns. There's some early work by Atkinson and Hutchison, 1978, using some simple analytic models, tried to understand what happens when you have this EUV gradient in the conductance. And it's primarily the Hall conductance that's important. The Pedersen conductance has very little effect on some of these rotation and asymmetries in flux circulation. And what Atkinson and Hutchinson found, and this was validated, I think, for the first time in a simulation by Ridley et al., a nice series of studies in 2004, you see a clockwise rotation of the convection pattern when you just put this gradient in the conductance on there, and you find more flux circulating in the dust cell. And I'll try to convince you in a couple of slides after this that the reason that this happens is that the ionosphere and magnetosphere, when they're working together, for some reason, try to minimize the divergence in the Hall current. Now, if you have a divergence in the Hall current, you can do two things. The system can do two things. It can send that divergence up or down the field line as field line currents to neutralize the charge that's going to accumulate there, or it can let the charge accumulate, build up a polarization electric field in such a way that causes things to rotate and moderates that divergence in the Hall current. The system seems to want to do the latter for reasons that I don't really understand. Okay, in another, more recently, Tian Lu at Dartmouth did some similar simulations to what Aaron Ridley reported using the LFM model, and imposed that same EUV conductance gradient only, no auroral conductance in this simulation here, and looked at some of the features in the magnetosphere. And so what you see here is that the reconnection rate, if you go, this is essentially the X line in a 1 hour average. If you march along the X line and you integrate the electric field along that line, you find that there's an asymmetry. On the day side, it's more or less symmetric, but on the night side, there's an asymmetry in the reconnection rate, and that reconnection rate produces fast flow. Color bar here is flow velocity, preferentially in the pre-midnight sector. So when the magnetosphere and ionosphere are shaking hands, they're both kind of exhibiting different kinds of asymmetry, but both consistent with each other. If you then map the convection pattern from the ionosphere into the equatorial plane, and you get about the same answer if you just calculate the streamlines along the average velocity field in the equatorial plane, you see something like this. This is really a curious effect. So these fast flows, and remember there's more flux circulating in the dusk cell than the dawn cell in this case. These fast flows come around, and some of that flux closes over in the pre-noon sector. So if you have, for example, more oxygen flowing out of the ionosphere in this region, that's going to come around and actually impact the pre-noon magnetopause over here. Okay, so in a study reported last summer, we actually put in both the UV gradient and an auroral gradient. This is from LFM's empirical conductance model, or precipitation model, which I'll talk about a little bit later. And so I contrast for you three cases here. So this is the case where the conductances in the ionosphere are uniform. In all three cases, the Pedersen conductance is uniform, not uniform, it's uniform here. Here, and what's plotted here is the Hall conductance, and so you see the EUV plus auroral, and then here, the great thing about simulations is you can do something that you cannot do in experiments in space. You can actually do bizarre things like dig a hole and make a Hall conductance hole in the auroral zone instead of an enhancement, which is the way the system really works. And when you do that, I think you see very convincingly that it's the gradient, and it's just the Hall conductance gradients again here, have a very significant effect on the asymmetries that you see in the magnetosphere. It reverses in this direction and in contrast with the case where things are uniform and everything's more Dungy-like, very symmetric. Okay. So what about the observational side of this? This is from a paper reported by Raj et al. 2002 in JGR. When perigee passes 95 to 97, they selected events in which the flow velocity in the neutral sheet, defined as the plasma beta greater than 0.5, were greater than 250 kilometers per second. When this simulation work I was describing was unfolding in kind of the mid-2000s, and I was visiting Tai Fan, who was the advisor of Raj in Berkeley, Tai's a friend, and I was telling him about what we were doing. He says, you know, we see these asymmetries in flows in the plasma sheet. We've been seeing them for a long time. And I said, well, I think the reason they're happening is because the ionospheric conductance is forcing the flows to go over to the side and change the reconnection rate. And he says, you know, we've been trying to figure out why this is happening for a long time, and I can't imagine, I could never have imagined that the ionosphere would do this. A little bit of chauvinism there in terms of the Magnetosphere-Ionosphere-Thermosphere interaction. And yet, the ionosphere seems to be playing a major role in controlling reconnection in the magnetosphere in this case, and its properties. And you see these things at lower altitude. Poleward boundary intensifications reported by Nishimura et al., preferentially in the pre-midnight sector. Those poleward boundary intensifications are also associated with this alphanic pointing flux that I talked about earlier, 6 to 182nd bandpass coming down, and broadband electrons that kind of produce the visible signature of the PBIs. These are part of that same system. Okay. So with some insights, not complete yet, into at least the electrodynamic aspects of the MI interaction, let me now go on and talk about storm and substorm processes and focus on a particular storm and do some more experiments to try and tease out cause and effect for you. So this is a fairly well-studied storm. It was studied by Crowley et al. Using time GCM, and they found that the BY dominant period, the green bar here, had the Joule heating associated with that enhanced the F region neutral density. This is not the plasma density, but the neutral density. And so for this initial phase from 6 to 9 in the green here, BZ is small and BY is dominant, 20 nanotesla, quite large. In the main phase, they're both very large, and the KP's 9 DSTs is a fairly significant storm. Okay, let's just go back and see what the Weimer model tells us the convection pattern looks like, and I've made a plot here in the pre-phase time when BZ was small, and in the main phase when both BZ and BY are large in magnitude. And you can see where KP is at this point. And you see, not surprisingly, strong BY. You see this pattern that we saw earlier. And then the rotation is more moderated here in the case when BY points in the other direction. We also have a strong BZ, negative. But remember, and so there's a disclaimer from Weimer, this model works best when both BY and BZ are less than 15 nanotesla in magnitude, where the bottom plot, actually both plots are outside that range. So one has to take these kinds of things with a grain of salt. And if you use Weimer or something model like this to drive an IT model for a storm, the fidelity of the convection may not be very good in that case. Okay, so Ben Zhang developed some simulations of the coupled Magnetosphere-Ionosphere-Thermosphere model, which we call CMIT. And the CMIT model basically takes the LFM numerical simulation. This is MHD, ideal MHD, and the magnetosphere describes well the solar wind magnetosphere interaction, reasonably well some of the night side dynamics, but not as well as the day side. And then coming out of this model, you can calculate or have proxies for the number flux, energy flux, convection, and also Ben has developed methods to calculate the broadband and other types of electron precipitation and ion precipitation, although the ions are not in here. These inputs are fed into the NCAR TIE-GCM. It ingests that information about the precipitation and develops a conductance, a conductivity actually, and then height integrated to get the conductance. And then that conductance can be used in the ionospheric equation that I talked about earlier in LFM. This is called the mix model. It requires also inputs from LFM in the field of line current, and then from here the convection is calculated, serves as a boundary condition, and this loop goes around. So this is the basic workings of CMIT. Now, the precipitation, these agents of MI coupling, so there are two different, broadly speaking, types of precipitation. So the monoenergetic and diffuse are described essentially by the Knight-Friedman-Lemaire relation, and we know that that works very well for this type of precipitation. We define an electron and density and temperature from the MHD values, choosing empirical parameters which define basically this 0.2 here is saying that TE over TI is about 0.2, which is a fairly typical number, and B characterizes how full the loss cone is in location. And we have a model for the resistivity in the gap region between the bottom boundary of LFM and the top of TiGCM, which calculates current voltage relation, which is used to determine the monoenergetic precipitation. Putting that in Knight-Friedman-Lemaire, one gets patterns for number flux and energy flux. One can run that through the Robinson et al. Empirical formulas for sigma p and sigma h. In a standalone LFM, in a CMIT version, tear this out and put TiGCM in there to get the conductances, and then come back here and loop around. For the broadband precipitation, it's a little bit different. So what's done is to extract bandpass filtered electric and magnetic fields in the 6 to 182nd band, like Keiling et al. Did for polar data, extract that from the simulation, use that in an empirical model that specifies the energy flux and number flux of broadband electron. These are soft electron precipitation based on those values. Turn the crank again, and once again, take this out and put TiGCM here in place of it for the standalone case. And so you have a whole other way of determining the conductance distributions in the precipitation and conductance distribution in the system. So what effects do these have? Well, so Ben did actually this is published in 2012 in a paper. So what you see here is the difference between two CMIT runs, one with and without the soft electron precipitation. Both have the hard precipitation, the diffuse and mono, but only one has the soft. And you see that you get a significant enhancement in the thermospheric density when you include the soft precipitation in this model. And I just want to mention some work, I think Ben and Uwe Dung kind of converged on this result at about the same time, coming at it from different ways. And so this plot doesn't really compare apples to apples here. Okay, so this is the difference between two simulation runs. What you see here is the difference, and this was a plot I showed earlier, between Champ's thermospheric density statistically determined over a year's worth of data and IMSIS, and at least it's suggestive that soft precipitation may have some impact on what's being seen here. But again, I just want to emphasize it's not exactly apples to apples. Okay, so now let's take the CMIT simulation and apply it to the storm, the solar wind data I showed earlier, and see what comes out of it. And so this is the initial phase that was studied using time GCM earlier by Crowley, and this is the main phase. And so the red curve is CMIT result, and the blue curve is the Champ data at each of these times. And so CMIT tracks Champ reasonably well for weak driving, particularly in this region here, but when the driving ramps up and you start getting a significant thermospheric response, it overestimates by a factor of 2 or more in some cases what Champ records. And so the question is, what's missing in the model during the main phase simulation? And things that we know happen, you get plasmaspheric plumes coming out, you get significant ionospheric outflows. Do those have an effect? So what we know about plasmaspheric plumes on Dayside reconnection, we know from both, these are both observational studies, Borowski and Denton and Walsh et al. And what you see in this plot right here is a case where the LFM simulation was initialized. I emphasize initialized. So this is not self-consistent with the ionosphere in the sense that the ionosphere is flowing out plasma to build the plasmasphere. At t equals 0, an empirical model for the plasmasphere is loaded into the simulation, spun up with northward IMF to get it co-rotating. And so that's what you see. This is after a 4-hour spin up at 5 nanotesla. And there are 3 contours, 330 and 3 per centimeter cubed contours in each of these plots. And then after that, after a 1 hour, when the IMF flips southward, you see a surge, so you get this convective surge, and you see a surge of the plasma sphere toward the whole Dayside, and that's actually been seen in image data, some of the work that Jerry Goldstein and collaborators have done. And this is at the end of the 5 nanotesla period, and you can see the whole Dayside plasma sphere has kind of come toward the magnetopause. And then in this simulation, and I'm not going to claim that this is the truth of how this happens, but after the IMF flips northward, you start to see this plume come out. The surge has subsided along the whole Dayside, and you see a plume, which is a well-known plume coming out of the plasma sphere, impacting the Dayside. And some of this observational work suggests that these plumes may have a significant effect on Dayside reconnection claim. Okay, I think those folks have backed off of that more recently to some extent. And so we know that the Dayside reconnection rate is smaller in a multifluid when the plasma sphere H+ is included. And the question is, if the plasma sphere is influencing Dayside reconnection, and Dayside reconnection shows up as the intensity of the convection in the ionosphere, and Joule heating, yada, 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 the whole chain, can that affect the F region neutral density? So we're gonna test that. Another pathway to get oxygen and ionospheric plasma, the plasmaspheric plasma is largely ionospheric origin, into the magnetosphere is through direct outflow of O+. The only source of that really is the ionosphere. And so Oliver Brambles and Bin Zhang developed a kind of an intriguing way to do this in a simulation, causally regulated. So they took fields at 3RE, calculated the fluctuating E and B, bandpass filtered them to get these patterns here, then got the AC pointing flux out of the simulation, mapped it down to 100 kilometers, implied what we call the poor man's ion outflow model. This is Strangeway's empirical model derived from fast data, providing a relationship between AC pointing flux, alphanic pointing flux, and oxygen outflow flux. And you put that into the, as a boundary condition in the LFM model. It's really poor man in the sense that while the flux is specified, we still need to say something about, if we specify a velocity, then we know what the density is and a temperature. So this is by no means a complete ionospheric outflow model. And Roger Varney and Alex Glasser have worked on ways to do this more consistently. Okay, so what happens when you do this in a simulation? So this result here is from storm time substorms. It's a famous event, April 18th, 2002. It's famous because there are probably, I don't know, 20, 30 papers published on this event trying to analyze various aspects of it. And the thing that's intriguing about this particular CME-driven storm is that it exhibits what are called sawtooth oscillations. Sawtooth oscillations are basically planetary scale oscillations in geospace that go through this oscillatory mode in which many features in the system vary quasi-periodically. And so the gray data here are geotail measurements of the estimates, I should say, of the open flux in the magnetotail in gigawebers. And so you can see that in the dashed lines give an indication where the sawtooth substorms go off observationally. And when you do a simulation without these causally driven outflows, they're absent. There is no sawtooth oscillation, no sawtooth substorm. When you include the causally regulated outflows, you get a quasi-periodic oscillation, but in these simulations, the tail dynamics are not truly faithful to what's going on in the tail. So while the period is about right in an average sense, the actual onsets deviate, and that's pretty much the case in any global simulation model. So these effects have been demonstrated to be important for actual events, and so it's reasonable to ask if they're affecting the whole dynamics of the system, is that also going to factor into the thermospheric neutral density? And so let me just mention briefly here what's going on here. So basically, the sawtooth substorm cycle, what happens is that the substorm goes off, and magnetic field lines snap, dipolarization, head earthward. There's a lot of pointing flux associated with that process that directs alphanic power, in particular, along the magnetic field lines headed earthward. When that alphanic pointing flux hits the ionosphere, some of it is converted into ion transverse acceleration, powers that process. Those ions now, through the mirror force, start heading up the field line, but they're slow. It takes them a half hour to an hour to get out into the plasma sheet. And it takes a while for them to build up, manifest their effects on the plasma sheet. And so on a period up from about an hour to an hour later, after the plasma sheet goes into a crisis situation because all this oxygen is coming out, another substorm goes off, and then the cycle repeats itself. Okay, alphanic pointing flux comes down, comes back. That's basically the process that we see in the simulation. It's hard to get at that in detail observationally. In fact, Magnetosphere-Ionosphere-Thermosphere coupling is a very hard thing to observe because there are so many internal machinations going on. Okay, so some controlled experiments, and I'm going to talk about some results that Ben Zhang has developed that are on the way to a better model, but this is the first step. So he did some runs with CMIT, loading in that Gallagher statistical empirical model for the plasmasphere, initializing it, so it's not sustained. If the plasmasphere goes flowing out to the magnetopause and is lost in the simulation, it's not replenished. There's no refilling. And then two different types of outflow. One, a polar wind-like outflow, relatively low energy coming out, fixed. Both of these outflows of O+ are fixed in time and space. So everything above 75 degrees is flowing out, O+, and actually, oxygen polar wind is not the dominant polar wind, it's hydrogen. But if oxygen polar wind isn't going to have much of an effect, surely hydrogen isn't either, okay? And then a population of auroral O+ coming out more energetically at lower latitudes in a fixed band in local time and latitude here. Okay, so comparison between various runs in CHAMP. So here we have CHAMP in blue again. Baseline, this is the same time series that I showed earlier without any outflow. The green line is if you include only a Gallagher plasmasphere, the kind of, I don't know what color that is, purple, auroral O+, and polar wind O+. And I should just mention that these outflow rates are consistent, at least statistically, with estimates of what the hemispherically integrated number of ions flowing out is. And so when you look at these various things, it's kind of hard to see on this plot because there are so many together here. But remember, CHAMP is blue, and I'll call your attention to the auroral O+. It seems to track CHAMP the best, and in fact, that's what this note says. Okay. So orbit average neutral density, a little bit easier to look at than looking at that time series of individual peaks. And so again, baseline, Gallagher plasmasphere, auroral O+, polar wind O+, and just to see what effect it has if we increase the flux of auroral outflow by a factor of 2, and then CHAMP again. And once again, you see that the auroral O+, with a reasonable value of the hemispherically integrated outflow rate, best tracks CHAMP in this case right here. Okay, some of the effects of O+ on MI coupling. First of all, the plasmaspheric H+ has little effect on the cross-polar cap potential and field line current, it turns out, at least in these simulations. And emphasize again, we're talking simulation world here. The polar wind outflow reduces the cross-polar cap potential, as does the auroral O+ outflow. So you can see here, compare baseline to auroral O plus and polar wind O plus, and they're both lower. So they reduce the cross-polar cap potential, and it's known in these simulations that the cross-polar cap potential is typically too high. So it's taking things in the right direction. And the hemispheric current is not hugely different for them, but there are some differences. But one thing that is quite different, if you look at pseudo-DST in these simulations, basically calculating the effect of all of the current systems in geospace at the center of the Earth. So it's a proxy for DST. The actual DST is plotted in black here, and you see that the auroral O plus, the more O plus you put, the more it pulls down DST. In these simulations, there's no true ring current. There is a diamagnetic current that flows like a ring current, but the ring current is actually a drift kinetic current, gradient curvature drifting. And so Alex Glosser, using the BATS-RS model, has shown, I think, very convincingly that it's pretty hard to get DST right in a simulation unless A, you have oxygen outflows from the ionosphere, and B, a good ring current model. And the ring current model that's used in these simulations is to couple the Rice convection model into the global simulation models. And then not only does DST come down, but it also tracks the time series better in that case. And so the auroral O plus, also, the hemispheric power for all the models is the same, but their distribution, more or less the same, but their distributions are quite different as you see here. So cross-polar cap potential on the top, field line current distributions, and these are hemispheric, this is the cross-polar cap potential, this is the distribution of potential or convection. Field line current, hemispherically integrated, Joule heat, hemispherically integrated, and thermospheric mass density at 400 kilometers. And so what you see is that the polar cap potential is smaller when you include outflow. Any kind of outflow, it helps. The region 2 currents are larger, and what that means is that it reduces the cross-polar cap potential because some of that region 1 current is now closing at lower latitudes into region 2. It doesn't have to close across the polar cap, all of it. And so the potential on the polar cap is lower in that case. And as a consequence, the distribution of Joule heating is different because of that closure, and you can see here in the case with the auroral O plus, you get stronger current closure out here where R1, R2 is closing and being fed by Pointing Flux, and this of course is just sigma PE squared here. And then the effect of reducing the potential and the speed of convection, particularly on the Dayside, is to reduce the Joule heating that goes into the thermosphere, and therefore the upwelling that you see at 400 kilometers due to that effect. Okay, so let me close here. And I have three slides, key points on some of the processes I've talked about. So auroral precipitation, this is the hard precipitation that goes down to the E layer and modifies the E layer typically. It increases the meridional gradient in the E region conductivity. The ionosphere polarizes in that gradient. That polarization effectively causes a rotation in convection. It exacerbates the dawn-dusk asymmetry, particularly during storms when you get a lot more charged particles being dumped into the ionosphere. And the asymmetry is very pronounced in convection, ionospheric convection, and in plasma sheet flows and many other parameters as well. And I think it's really an outstanding question as to why the MI system prefers to maintain a near zero divergent Hall current rather than diverting it into field line current. There's some hints in the literature that it may have something to do with maintaining a minimum dissipation state. So it's kind of like the solar wind magnetosphere interaction and the night side interaction basically acts like a current generator. It's only going to supply so much current. And therefore, if the ionosphere says, look, I can get rid of this divergence in the Hall current if you just give me some more field line current, and the magnetosphere says, nope, can't do it. So the system polarizes and does that. And, so locally, that rotation generates an additional Pedersen current, and therefore locally enhances the Joule dissipation. But some calculations suggest that globally it actually minimizes the Joule dissipation there. Is that really true? Is that really how the system works? We don't know. Soft precipitation, electrons. These are produced mainly by direct entry from the cusp. Magnetosheath electrons are relatively low energy, and also conversion of Alfvén wave power to field line electrons, both dayside and nightside. It enhances the conductivity on the bottom side F region, not down in the E region, but bottom side F region. And that enhanced Joule heating tends to elevate the mass density that's seen at champ altitude, but it elevates it too much if that's the only effect that you include in these simulations. With regard to the ionospheric O+ outflows, they lower the reconnection rate in a variety of ways, and they do it both on the day side and on the night side. That produces a lower cross-polar cap potential, slower convection in the ionosphere, less Joule heating, especially in the polar cap, which finds its way into, or as a reduction into the thermosphere and enhances the profile. And auroral outflows seem to have the greatest impact. And the reason for that is actually twofold. Auroral outflows, when they come up, relatively, if they're not too energetic, they come up and they start circulating around, and they actually populate what's called the warm plasma cloak. This is a term that Rick Chappell invented, and populates the whole dayside magnetosphere. And when you get this convective surge, it's that warm plasma cloak that goes out and hits the magnetopause. And the reconnection rate's basically proportional to the Alfvén speed, and if you have heavier ions, the Alfvén speed's lower, reconnection rate's lower, and so on. So that's one way it affects it. The other way that the O+ outflows affect the reconnection is by flowing out on the night side directly toward the night side X line and changing the dynamics of reconnection there as well. What we don't know, and this is really an indirect way to modify the thermosphere. In other words, it's very circuitous. Outflow, modify reconnection, change convection, change Joule heating, right? Is there a direct effect? And I don't think our models are good enough to know yet, but when you start sending lots of oxygen out, does that modify the thermosphere? We have I think we have a pretty good idea is that when the thermosphere is elevated, for example, during solar min and solar max, the flux of thermal outflows, polar wind, is different. So the thermosphere can clearly have an effect, but do these outflows directly affect the thermosphere locally as opposed to this circuitous route? Thank you.